So in lecture 17, we start looking at a system of linear first-order differential equations. And at this point, we just go over some concepts, some definitions, and theorems related to system of differential equations. One of the main point of this lecture is, like, when you get a solution, you want to know if the solutions are linearly independent with one another or not. And the key to do that, or the concept to do that, is to use or calculate the Wronskian to determine, like, when the Wronskian of the solutions are different from zero, then you can say that the solutions or the solution vectors are linearly independent. And then in addition to that, we can conclude that the set of all the solution vectors form a fundamental set of solutions of the system of differential equations. And for whatever system we're working on in the course, we try to make it easy so that we can always find the solutions. And the solutions that we find are linearly independent. Therefore, there's always exists a fundamental set of solutions for the homogeneous system on the interval I. Right? So that's the concept of theorem 4. Now moving on to theorem 5, when you have the general solutions of the homogeneous system, and later on we have another theorem on the general solutions of the non-homogeneous system. Okay. So let's say that you have a fundamental set of solutions consists of x1, x2, x3 up to xn. In other words, you want to let vector x1, x2 up to xn be a fundamental set of solutions. Of the homogeneous system. X prime equal to a times x on the interval I. Then the general solution of the system on the interval is, so x equal to c1 times x1 plus c2 times x2 plus up to cn times xn. Right, so this particular formula or equations or functions you have seen before already. Right. Assume that you have some solutions, x1, x2 up to xn, and they are linearly independent. And therefore, the general solution is just linear combinations of all of the solution vectors. Right. And we want to test that, where c1, c2 up to cn are arbitrary constant. So moving on to the example. So example 5, I'm going to use the information from example 4 that we have this two solutions vector, x1 and x2, that satisfy the system or homogeneous system that we see earlier up here. Let me see, somewhere here. So back here, so these two solutions satisfy this homogeneous system. Okay. And so we check that x1 and x2 are the solutions to the system in example 2. And in example 4, we show that the two solutions x1 and x2 are linearly independent by calculating the Wronskian between the two solutions vector. Right. And now in example 5, I'm going to write down the general solutions of this homogeneous system. So we know that x1 equal to e to the negative 2t minus e to the negative 2t, and x2 equal to 3 times e to the 60, 5 times e to the 60 are linearly independent solutions. Of the system x equal to 3, 3, 5, 3, e to the, sorry, this is x prime, this is x, this one is 1, so 1, 3, 5, 3. So again, I want to know that we have this result from example 2 and example 4. So from example 2 and 4. Alright. So with this result, we can conclude that the general solutions of the system on the particular, on the interval of consideration is going to be the linear combinations of x1 and x2. Then the general solutions of x1, sorry, of the system is So x equal to c1 x1 plus c2 x2 equal to c1 times 1 negative 1 times e to the negative 2t plus c2 times 3 5 e to the positive 60. Again, I just want to show you mostly for this lecture is just concept definitions, the kind of denotations, and how you could obtain or how you write the solution in certain way, right? So as you can see here for x1 and x2, you can always pull out the e to the negative 2t for x1, and you can pull out the e to the 60 for x2, right? So it doesn't really matter how you write it. It just, when you write the general solution this way, it just looks nice. And then later on in sometime next week, you will see that sometimes it's actually more convenient to write the general solution in this form, right? With the coefficients vector 1, negative 1, and 3, 5 written like this. Okay. If not, I'm going to move on to example 6. So in this example, I want to do some quick calculations on the Wronskian of this system of linear first order differential equations written in the form of x prime equal to 101, 110, negative 20, negative 1 times x. And it's given to us that the system have three solutions, x1, x2, and x3. And we want to know if these solutions are linearly independent or not. Okay. So to see if the solutions are linearly independent, we need to calculate the following. So we have the Wronskian of x1, x2, x3 equal to the determinant of cosine of t, right? So all of these three solutions are column vector. So when you calculate the Wronskian of x1, x2, x3, you just plug in the column vector. Okay. So the first column is for x1, so cosine of t, negative 1/2 cosine of t plus 1/2 sine of t. And the last entry is cosine of t minus sine of t. The second column is for x2. So you have 0, e to the t, 0. So I just slide e to the t into the vector, or multiply the vector by e to the t. And the last column is for x3. So that is sine of t, negative 1/2 sine of t, minus 1/2 cosine of t. And the last entry is negative sine of t plus cosine of t. So that's the setup. Right, so this is a 3x3 determinant, which you can start with any rows or columns. Right, doesn't matter. The more zero on the column or row, the better. Right, so I'm going to choose to work with the second column here because I have 2, 0. Right, because with the entry 0, you don't have to calculate corresponding 2x2 determinant. So this is 0, this is 0. Right. Now you look at the sign of the coefficients that you choose to work with. So this is positive, this is negative, and therefore this is positive. So the sign alternates between the coefficients. So positive and negative and positive. So you have e to the t. Right. Okay. When you choose to work with a to the t, you delete or you remove the corresponding column in the corresponding row. So you delete this column, in this row, and you're left with the entry of cosine of t, sine of t, this one and this one. Okay. So you're left with a 2x2 determinant. That is cosine of t, sine of t, negative cosine of t minus sine of t. And the last entry is negative sine of t plus cosine of t. From the 3x3 determinant, you turn that into a 2x2 determinant only. So it's easier to calculate. So this is e to the t times cosine of t times negative sine of t plus cosine of t minus sine of t times negative cosine of t minus sine of t. Inside the big parentheses, you just distribute or FOIL everything out, and then cancel things out if you can't. Okay, or combine like terms for that matter. So here, from the outside, you have e to the t. From the inside, you have negative sine of t, cosine of t, plus cosine squared of t, plus sine of t times cosine of t, plus sine squared of t. Again, inside the parentheses, you can see, if you notice, that this term and this term cancel out, And you're left with cosine squared of t plus sine squared of t. And that is the trigonometric identity that is equal to 1. So therefore, the calculations give you e to the t only, and this is definitely different from 0 for all real values of t. And from these calculations, we can definitely conclude that x1, x2, and x3 are linearly independent. In addition to that, they form a fundamental set of solutions. Okay, so we conclude that x1, x2, and x3 are linearly independent. In addition, they form a fundamental set of solutions. Because of these conclusions, we can write down the general solutions for the system, right, which is the linear combinations of x1, x2, and x3. So therefore, the general solutions of the system is x equal to c1 times x1 plus c2 times x2 plus c3 times x3. Again, it's just linear combinations of three solutions that we got. Okay, so that's the general solutions for the homogeneous system. Now we're going to move on to the next theorem for the general solutions of a non-homogeneous system. And you know it, there should be two types of solution in the general solution. The first one is the complementary solutions or the homogeneous solutions that is corresponding to the homogeneous system. And the second type is the particular solutions for the non-homogeneous part. Okay, so let's accept P. Be a given solutions of a non-homogeneous system. X prime equal to a times x plus f, right, on the interval I, and let x sub c equal to x1 c1 x1 plus c2 x2 to cn xn denote the homogeneous solutions. On the same interval of the associated homogeneous system. X prime equal to a times x, then the general solutions of the non-homogeneous system is x equal to xc plus x sub p. X sub c is the homogeneous, let's say complementary or homogeneous solutions, and x sub p is the particular solution. Okay, so again, as you can see, it's very similar to what we have before, right, when we talk about homogeneous differential equation. Right? For the non-homogeneous differential equation, you have the homogeneous solutions and the particular solutions. And then you add them together, you get general solutions for the non-homogeneous differential equations. Now, when we move on to the non-homogeneous system, it's the same thing. You need to find the homogeneous solutions for the system, for the corresponding homogeneous system, and then the particular solutions. And then you add them together, and you get the general solutions for the non-homogeneous system. Okay. So example 7, I'm going to demonstrate that. So all of the solutions are given to us. Eventually, we will learn how to formulate this type of the solutions. But for now, for the demonstration of the concept, all the solutions are given to us. Okay. So the vector x sub p equal to 3t minus 4, and this is negative 5t plus 6, is a particular solutions of the non-homogeneous system. So that is x prime equal to 1, 3, by 3 times x plus the non-homogeneous part of t minus 11 minus 3. Now, if you don't have this part of the system, if you don't have the non-homogeneous part of the system, then this is the homogeneous system. Right? And for this homogeneous system, you know the solutions. That's it. You can go back again, look at example 1, example 2, example 4, and example 5. So the complementary solutions. Well, this is homogeneous solutions of the homogeneous system. Is x of c equal to c1 times 1 negative 1 times e to the 2 t, negative 2t plus c2 times 3, 5 times e to the 16. So again, we go back to example 5, example 2, example 4, and example 5 to see this equations. So quick note here. We go back to example 2, 4, or 5 to see the result. So you got the particular solution, you got the homogeneous solutions, therefore you can write down the general solutions. So hence, the general solution of the non-homogeneous system is, so we have x equal to c1, 1 negative 1 times e to the negative 2t, plus c2 times 3, 5, e to the 6t, plus the particular solutions of the form 3t minus 4, negative 5t plus 6. I'm going to stop right here for lecture 17. I'm going to move on to lecture 18. As I mentioned earlier, lecture 18 will involve a lot of graphs, right, where we talk about direction field and solution curves.